Welcome to my projectbazaar.com. Let us discuss about the broadband dual-polarization and stable-beamwidth slot antenna feed by U-shaped microstrip line. Let us discuss about the abstract of the product. Satellite technology is developing fast and the application for satellite technology are increasing all the time. Not only all satellites can be for radio communication and many more applications. The rectangular patch loaded with U-slot antenna is designed for WLAN and WiMAX application. The slot antenna concept has been used in patch antenna design to maximize the return loss and reduce the antenna size. The dielectric substrate is 4.4, that is a FR4 substrate is used in this fabrication. The return loss bandwidth of the proposed antenna are calculating by using the MATLAB software. So in this paper, characterized mode analysis of 3 empirical design techniques for probe field symmetrically loaded, and then the U-slot microstrip patch antenna on a single layer grounded substrate is presented with supporting the experimental data. The first method is a resonant frequency, and the second one is a dimensional invariance, and third one is a both of the resonant frequency and dimensional invariance. So in both these methods, the optimization of the probe location is necessary for further enhancement of the 10 dB return loss bandwidth, because the return loss should be in minus 10 dB only. The third method, dimensionally invariant. So the optimally combines a feature of previous two is developed here, and so to yield the bandwidth performance with minimal or no probe location optimization, and hence is superior to the other two for rapid prototyping. CMA is carried out for the critical parameters such as a substrate electrical thickness, slot width, probe radius, and field location variance to access the dominant end lines on the characteristics of U-slot microstrip patch antenna. Let us discuss about the flow diagram of the process. First of all, the antenna should be designed and calculating the parameters for the design, and then assign the center frequency of the particular antenna, and then solving the RLC circuit and find the return loss, and finally calculate the performance. So I will explain the one by one procedure for the flow diagram. First of all, there is the antenna design. So basically the antenna design, like this. This is a side view representing the layers of the antenna. First of all, the antenna design, this is a patch, and this is a substrate, and this is a coaxial probe. Finally, this is a ground plane. So the patch of the antenna, we draw the microstrip patch or anything else. In the patch of the antenna, we using the U-slot and then design the probe. It's a substrate. Moreover, there are many materials. Here we use FR4. So the FR4 dielectric constant is 4.4, and then the coaxial probe feed is calculating the value of ground plane, and then the coaxial probe is analyzing the wave port of the design. So that is calculating by the ground plane. So in this antenna design, we using, this is the substrate. So this is the patch, this is a rectangular patch. Here we using the U-slot, that is a single U-slot of the antenna. In bottom of the substrate, here we use the coaxial probe feed, that is very useful for the mostly antenna. Here we use the coaxial probe feed only. So that is all about the antenna design, and then the calculating parameters for the design. And the calculating parameter of the design is there is a critical parameters, that is a substrate electrical thickness, slot width, probe radius, and field location variance. There are many parameters, that is a length, width. For all the calculating parameters of the design, calculating in our MATLAB, and then assigning the center frequency. Normally the frequency is calculating in the antenna. Center frequency is also known as operating frequency. Here operating frequency is 1 GHz to 4 GHz antenna. So here we calculate the antenna as 2 GHz as assign the center frequency. So this is a type of a center frequency we calculate assuming F0. F0 is a 2 or related to nearly to the 2 of the antenna. Next is solving the RLC circuit for related to the antenna design. Mostly rectangular patch antenna, like the RLC circuit is same or R and L and C, that is serially connected in the circuit. So that is solving to find resistance, inductance, and the capacitance. So this is the RLC circuit, R1, L1, and C1. So resistor, inductor, and capacitor, that's our serially and parallelly connected with the RLC circuit. To solve the RLC circuit, we find the R1, L1, and C1. The equations are, so these are the equation for R1, L1, and C1. So H is the substrate thickness. Likewise, R1 is the resistance, and QT is a probability of the function. FR is a center frequency. So these are the description of the equivalent circuit. And then finally we calculated the return loss. Return loss is S11. all over the return loss is always should be less than minus 10 dB. That's only the antennas to be operating. So the return loss is calculating by using the solving the RLC circuit. Finally we're getting the RLC is the performance analysis to compare all the results for existing and proposed. So finally calculate the return loss and radiation pattern of the antenna. So that's all about the flow diagram of the process. Yeah, let us also discuss about the running procedure for the product. Click the main file and run. Yeah, in this figure 1 graph, this is the frequency that is denoted by Addons, that is 10 power 9, and this is the return loss. Return loss is displayed by the dB, so that is a decibel. So 0, minus 10, minus 20, up to minus 50. These are the return loss of the dB. The frequency range, that is 1 to up to 4. So these are the frequency range. In this first is all, this is epsilon r is equal to 4.4 for the dielectric constants for the FR4 substrate. So that graph, I'm getting the plot like this. For up to this number, this is a minus 10, minus 20 is a minus 30, and for 0, these are the 9 points for the epsilon r 4.4, 4.4, and this plotting is for epsilon r is equal to 4.4. So compared to this, this is a low return loss, so this is a maximum return loss we get. Epsilon r is equal to 4.4. so this is the description of this figure. Yeah, in this graph, that is also getting a return loss, but changing the dimension of the rectangular patch. So first of all, size reduction of the rectangular patch, we get this, and then we increase rectangular patch size and we get this graph. So S11 is compared to this one is a very maximize return loss we get, and this one is a low return loss and get. So the frequency is up to GHz and 10 power 9, and return loss is 0 to up to minus 50. So this best performance of this FR4 is equal to 4.4. And then we calculating a 3-dimensional plot and 2-dimensional plot. 3-dimensional plot like the radiation pattern. For a 2-dimensional plot, that is also a radiation pattern. Here we click the 3-dimensional plot. So this is the radiation pattern of the graph. So the red is denoted by the high frequency, and yellow and blue and yellow green. So this is the 3D dimension pattern of the radiation pattern. Again we click the 2-dimensional plot. In this 2-dimensional plot we can get like this. So this is the 2-dimensional plot, like a half wavelength dipole. So at pi is equal to 90 degree. This is the x-axis and this is y-axis. Normally we get the dimensional plot like this in the MATLAB. For HFSS we get the complete graph of this. So in this MATLAB we getting like this only. So this at pi is equal to 90 degree. Also we find also pi is equal to 0 degree or pi is equal to 180 degree. So these are the procedure for the these are the running procedure for the product. Thank you for listening this video.